Good morning, class. This is Professor Munoz here, and I'll be going over a motorcycle jump problem where we'll be finding the initial velocity, the time spent in the air, and the angular velocity of the front tire at this instant. So this is our problem here. We have a jump going off at 32 degrees. We want to clear a total of 13 feet. So the first step here is to use one of the kinematic equations in the y direction. So we have y equals y naught plus v naught times t plus 1/2 at squared. So I made the problem, I simplified it. This is a line this is my data line here, and I'm going to leave it at this height here, and I'm going to land at the same height. So that's why y and y naught go to 0, because they're the same. Then I have v naught in the y direction times t. We get v naught by breaking down v naught into its x and y components. In this case, in its y component, we have v naught times sine theta, where theta is 32 degrees. We end up getting 0.5299 v naught. We get this value that we found here, put it into our v naught, and then we go, for our acceleration, in this case, it's gravity. It's a negative 32.2 feet per second squared. We multiply that times the 1/2, and we get the negative 16.1 feet per second squared. Okay, so now we have our equation here, but I have two unknowns. We have v naught as our unknown, and we have the time t as our unknown. So we have two unknowns, so that means we need two equations. So I'm going to call this equation here will be equation 1. And now we need to do another equation to get rid of our v naught or get rid of the t, where in this case we're going to get another equation in terms of t, and I'm going to pass that on to Professor Jordan.
So I'm going to pick up where Eddie left off, and I am going to use a kinematic equation in the x direction. So first off, our x naught goes to 0 because we start from a fixed position. Also, our acceleration goes to 0 because we have a constant velocity. So once we simplify this equation, we are left with x equals v naught times t. So we know we know our distance, which is 13 feet, and we know our velocity, which is the 0.848 v naught, and that came from breaking down the velocities in the x and y direction. So once we did that, we solved for t. Now that we solved for t in equation 2, we would plug equation 2 into equation 1. Once we plug everything in, we know our v naughts cancel out, and we are left with the 0.5299 times the 15.33 feet. Once we do that, we do the minus 16.1 feet per second squared times the 15.33 feet over v naught squared. That leaves us with this right here. That leaves us with the 8.123 feet minus the 3,783.64 feet cubed over second squared, divided by v naught squared. Now we want to set those two equal to each other so we can solve for v naught. Once we set those two equal to each other, we can solve for v naught, and we are left with v naught squared equals the 3,783.64 feet cubed over second squared, divided by the 8.123 feet. After doing the math for the units, we are left with the feet squared over second squared. Once you take the square root, we will be left with feet over seconds, which is the velocity.
Alright, so now I'm going to take over where Jordan left off. He had found that v naught is equal to the square root of 469.79 feet squared per second squared. When we do the square root, these squares cancel out, and we're left with v naught is equal to 21.67 feet per second. And that's our initial velocity. Now that we have our initial velocity, we want to find the time spent in the air. Jordan previously also found equation 2, which t is equal to the distance x divided by v naught, where x was equal to 13 feet, and the initial velocity found from this value, 21.67 feet per second. Here, the feet cancel out, and the time equals 0.599 seconds. and we found two of the values that we wanted to find previously. Now we need to find the angular velocity. So here we want to find the angular velocity of the front tire. This front tire has a diameter of 21 inches and a velocity of 21.67 feet per second. The way we're going to find that, we're going to do velocity equals omega times the radius. The velocity found previously is 21.67 feet per second equals omega times 21 inches divided by 2. It's divided by 2 because the diameter is 21 inches and we want to find the radius, so we got to divide it by 2. So what we're left with is 10.5 inches, but we want this inches in terms of feet, so we got to convert it again, do the 10.5 inches divided by 12 inches to get 0.875 feet. So now we're left with 21.67 feet per second equals omega times 0.875 feet. Divide the 0.875 feet to both sides, and we're left with omega equaling 24.76 rads per second. But we want those rads per second in revolutions per second. So what I'm going to do is do another conversion, and we're going to divide it by 2 pi radians. So when we do that, we'll get omega is equal to 3.94 revolutions per second. Cool.
That's it. Dude, that was perfect. Literally your back tire hit right here. This is you. That's you. The back of your tire. That's our 13 feet. Jeez, man.
All right, so the edge of the jump. Let's see here. Watch your finger. I got you. It's right about 32 or so. We'll see.
32.
Yeah.
32.
Yeah. Okay. Okay, so here's the jump. We're gonna measure where I landed at, so we can calculate my speed and the time. Hold it pretty straight.
Well, like 25.
I've really just been studying everything I'm taking notes on.
See? So right here we got indication that it's a 21-inch rim. We have a pink line here to see how many revolutions it'll make in 1 second.
Alright, we're good.
So I'm here actually editing the video, and I found a pretty good way to see how many revolutions the front tire is going to make. I'm going to play the video and then stop it and then break it up into quick little segments and see how many revolutions the front tire is going to make over 1 second. So here we could see how much is going to go in 1 second. So let's find a good spot here. I knew there was one like around 13. I nodded my head, and I think that's what they gave me the signal. I was going the correct speed, which is 15 miles an hour, roughly. Okay, there it is. So I want to look for the pink dot here. I'm gonna see, there it is on the front tire. So that's a good spot. It's at 10.4 seconds. So we're going to go to 11.4 and see how many revolutions it makes. So let's go break it in steps here. That's 1 revolution. Kind of hard to see, but that's 2 revolutions. We're going to keep going here. It's about 3. Okay, so we went too far. So it was about 3 1/4 revolutions. Alright, so I'm going to go over the percent errors. And here we have for velocity, we have it for time, we have the angular velocity, and then we have the distance. So first I'm going to go with velocity. The theoretical velocity that was found was 14.77 miles per hour, and the actual was 17 miles per hour. Our percent error was 15.1%. I believe this is due because we did not calculate for wind resistance, which means I have to actually go faster to clear a certain distance than the one theoretically solved. Next, the time. The time that we solved for was 0.599, and the actual time was 0.47 seconds, and we got an error of 21.5. So the reason for this error is because there might have been a bad calculation on getting the angle of the jump, so which means it wasn't as steep as we predicted, which means that I came back to the ground a lot quicker. Next, the angular velocity. We did the angular velocity calculating the actual theoretical, and we actually were going at 14.7 miles per hour on the street. So our error was actually 20.7%. I think this is due because I'm actually using a digital GPS speedometer, and it says that I was going 15 miles an hour, but there could be some error to that. I might have been going a lot slower. I might have been going more like 14 miles an hour, so that's why we get such a 20.7 error. Next was the distance. Again, the distance was probably due, I came up 3 inches short than the actual distance calculated. This is probably due because it was a little bit windy outside, and also for my body and the motorcycle having wind resistance. So that's what we get, 0.769. It was very close. This is probably our most accurate calculation. So thank you very much for watching our video.